So, but no further ado, let me just introduce the very last speaker for this session, which is Zohreh Kazemi Motlagh from the New Mexico Institute of Mining and Technology. And she's going to be telling us about the geochemistry of critical minerals and mine waste in Grant, Sierra, and Socorro counties, New Mexico. Thank you very much.
Thank you for the introduction. Hello, everyone. My name is Zohreh. I am a PhD student from New Mexico Tech, and today I want to share one of our ongoing projects at New Mexico Bureau of Geology and Mineral Resources in New Mexico Tech, which is titled Geochemistry of Critical Minerals in Mine Waste in Grant, Sierra, Socorro, and Socorro counties in New Mexico. My co-authors are my research advisor, Dr. Virginia McLemore, and Evan Owen. I'd like to start my presentations with acknowledgements, which is the most important part of each project. Thanks to Dr. Timmons, who is the Bureau Director and State Geologist. I'd like to send my big thank to USGS EarthMRI for funding this project for mapping of the Blackhawk area and critical minerals in mine waste. Support for the XRD work was provided by the DOE award to John Rakovan, and thanks to Jacob Newcomer, who did the XRD analysis. Thanks to Sarah and Abina for their assistance in doing the page test, as well as, and the last but not the least one is thanks to Dr. McLemore's Economic Geology Group and Magdalena Teen Science Cafe for their assistance in collecting samples. Critical minerals, the hot topic of these days. Starting from the scratch, critical minerals are non-fuel minerals that are essential to the U.S. economy and national security, whose supply may be disrupted. These minerals serve an essential function in manufacturing a product, and the absence of each may have an essential consequence for the U.S. economy. Here is a periodic table which is showing critical minerals in New Mexico. This list may differ from country to country, and even within a country, it may change yearly. For example, potash and uranium have been removed from the list in 2022, and nickel and zinc were added. And the most recent one by DOE is the copper, which is added by DOE and not the USGS yet, which means each mineral and commodity have the potential of being critical in the future, depending upon the use and availability. Mine wastes are potentially important sources of critical minerals because in the past, in the original mine, particularly the base metals and not the critical minerals have been produced. The focus of this project is on three different deposit types. One of them is the copper flat, which is in the Sierra County, in the Hillsborough mining district in Sierra County. Copper flat mine is a small copper porphyry deposit. In 1982, from March to June, the Continental Mineral Corporation has been produced significant amount of copper, gold, moly, and silver from the district before declaring the bankruptcy and ceasing the production. Next one is the Kelly mine in the hills in Magdalena district in Socorro County. The district is located on the west slope of northern Magdalena, near the Socorro. The district has been produced significant amount of zinc. They were produced from 1904 to 1928. The district produced 46% of total zinc that has been produced in New Mexico, as well as 34% of total lead. And the last one is the Blackhawk district, which is located in the Grant within the Bro Mountains. The district is an arsenide 5 element vein deposit type. Those hydrothermal veins contain silver, nickel, cobalt, bismuth, and arsenic, along with local uranium, base metals, lead, copper, zinc, and others. Our samples include tailings. Tailings are materials back from the mill, mine waste rock piles, which are ore grades that their grade is below the cutoff grade, and water. The purpose of this project is to provide data on 3 different districts in New Mexico and characterizing and estimating the critical minerals in mine waste, as well as determining the asset generating potential to provide information to support the planning of future mining operations in these areas. To reach our goals, we followed the USGS sampling procedures. We sampled the soils and sieved them and separated them as fines and coarses. Also, within each feature, sometimes we needed to composite the cell samples. So also, we selected some certain areas. We selected the veins and outcrops that we had in those areas. Also, we did the profile sampling where feature was eroded. When sample preparation occurred, we sent out our samples to the ALS and the USGS laboratories to identify the geochemical analysis of our samples. To assess how our samples behave subject to weathering conditions, we did the paste pH test and the FIS test. And to identify the mineralogy of selected samples, we examined them under the microscope. Also, we took advantage of doing XRD. And the results, this spider plot is showing the chondrite normalized rarest element plot of our samples. Black are the Black Hawk samples, green is the Black Hawk samples, red are the samples from Copper Flat Mine in Hillsborough District, and the blue is the samples from Kelly Mine in Magdalena District. As you see, our samples are slightly enriched in light rarest elements. And for example, the Black Hawk, which is the green one, is 400 to 500 times enriched in light rarest element. In the mine waste, in the copper flat tailings, we did the profile sampling. We sampled that tailing based on different colors or different textures that we had. These downhole plots could be useful for the remediation plans to identify the distributions of contaminations and so on. And as you see, by increasing the depths from left to right, we have the concentrations of sulfur, copper, and tellurium increase. Continuing with the geochemical analysis from copper flat mines, our tailing samples are enriched in bismuth, copper, zinc, and zirconium. For example, the average concentration of copper is 1533 ppm, and by assuming a bulk density of 1430 kilogram per cubic meters, we will have at least 1,400,000 kilogram of copper. For the Black Hawk samples, we separated the samples as fines and coarses by sieving them to compare the concentration, different concentrations that we had in our fine and coarse samples. As you see, and these box plots are using the difference between the variability and the average of those concentrations in fines and coarses. For example, for the lithium, the concentration, there isn't a big difference between the concentrations of lithium in fines and coarses, but regarding the titanium oxide, niobium, and yttrium, our samples were much more elevated in fine samples rather than the coarse. We took two of our Black Hawk samples, those mine waste samples, and we did the particle size analysis to compare our size fractions with the value of our elements. And as you see, the concentrations of nickel, cobalt, copper, and arsenic, they increase as we had the finer size fraction. Having said that, the Black Hawk samples is an arsenide 5-element vein deposit that contains silver, nickel, cobalt, bismuth, and arsenic. And as you see, our ore samples are how high grade our ore samples are in arsenic, cobalt, nickel, and cobalt. And our mine waste samples are even enriched in silver. As you see, our silver is not a critical mineral, but it's always a precious metal and it's always a look after. Some of our samples were elevated much more than 200 ppm in silver. And for the Kelly mine, our samples are enriched in copper, zinc, indium, and lead. And for example, the coverage of copper grade is even more than the copper flat minings, which is a copper porphyry deposit, and it's up to 2136 ppm. Having said that, to assess the behavior of the geochemical behavior of our samples, we did the paste pH test, and when we measured the paste pH, we did some static tests to predict the acid generating potentials of our samples by comparing their maximum acid generating versus their maximum neutralization potential. And these combined acid drag drainage classification plot is showing how our samples will behave. For example, the black arc samples, which are the green one, all of them were non-acid forming, but some of the copper flat in Hillsborough district and some of the kaolin samples in Magdalena district, they were producing acid. They were in potentially acid forming quarter. So the presence of critical minerals in mine waste could be of economic interest. For example, the copper flat mines in Hillsborough district, those tailings are elevated in bismuth, copper, gold, copper, cobalt, gallium, tellurium, zinc, and zirconium. And those downhole plots showed that there was a correlation between the depths and the concentrations of sulfur, copper, and tellurium. And for the Magdalena district samples, our mine waste, those rock pile samples are elevated in copper, zinc, and lead. For the Blackhawk mine waste samples, those mine waste samples are elevated in silver, cobalt, barium, copper, nickel, zinc, and total rare earth elements. And regarding the concentrations of their concentrations in fines and coarse, our samples were more elevated in niobium, titanium, and yttrium. And the particle size fraction geochemistry showed that the finer sample we had, the more concentrations we had for silver, cobalt, arsenic, copper, and nickel. And determining the acid generating potential showed us that our Blackhawk mine waste samples are in non-acid forming quarter, which means that we can use them for further purpose, such as backfilling materials. But the highest in some samples from Magdalena district, as well as the Hillsborough district, they are acid forming and can potentially cause acid mine drainage. So we need to do further analysis before using those, because the pH level can influence the variability and availability of some of our critical minerals and rare earth elements, and also they will cause some environmental issues.